An asynchronous method for cloud-based rendering. Graphics hardware has progressed to provide small, low-power devices like mobile phones and tablets with the ability to interactively render high-quality graphics. On the other hand, when it comes to high-fidelity interactive rendering, these devices fall short of providing the necessary computational power for visualizing phenomena such as dynamic global illumination. Cloud-based rendering techniques have somewhat mitigated the problem by moving the computational burden of rendering to remote servers and streaming the output as a video. Cloud-based rendering applications, however, have a number of shortcomings. For instance, in highly interactive applications where low latency and fast response times are of the essence, network fluctuations may introduce input lag and disrupt user experience. This is especially true of virtual reality applications, where high frame rates coupled with highly responsive rendering feedback are essential for a comfortable experience. Furthermore, cloud-based applications are heavily constrained by the bandwidth available to a user and the stability of the interconnecting network, which determine the video stream quality at the user's end. Bandwidth requirements grow with frame rate, resolution, and dynamic range of the video stream. However, the cloud's potential to offload expensive computation is too valuable to be ignored. It can still be harnessed in ways that still mitigate these issues. In this work, we present a novel rendering method that aims to eliminate input lag and mitigate excessive bandwidth requirements, frequently present in other cloud-based rendering services. Rendering is distributed between the cloud servers and the client device, apportioned by computational complexity. In particular, we separate direct and indirect lighting computation, moving the latter to the cloud. On the cloud server, irradiance for the indirect lighting is computed at regular intervals. It is then synchronized with client devices on demand. For every frame, the client device uses the local view-independent lighting cache to reconstruct the diffuse indirect lighting and combine it with the locally computed direct lighting to give the final composite that is presented to the user. We refer to this method as Remote Asynchronous Indirect Lighting, or RAIL. RAIL requires an automatic one-time pre-computation step to generate a point cloud representation for the scene used to sample indirect lighting. Indirect lighting is continuously kept up-to-date server-side. Virtual point light tracing is used to approximate indirect lighting as point light sources. Irradiance is then computed from these sources at each sample position in the point cloud. Irradiance samples are stored in a view-independent data structure termed the irradiance grid. On demand, this grid is partially streamed to the client device, which uses it to reconstruct indirect lighting. First, geometry-aware interpolation is used to reconstruct the luminance channel of the indirect lighting component. Luminance is then modulated by the albedo channel to fully reconstruct diffuse indirect lighting. For dynamic objects, the grid is used to generate a spatially varying ambient function that is modulated through ambient occlusion. The resulting indirect lighting, both for dynamic and static objects, is combined with direct lighting to achieve the final image. In collaborative virtual environments, such as multiplayer games, the cost of computing indirect lighting is amortized across the number of connected clients. RAID server computation is amortized across multiple connected users. Indirect lighting is only computed once and shared with all the clients. RAID Cloud Service integrates into Unity 3D for remote asynchronous computation of indirect lighting.